This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Hey, this is Jeremy Jung for Software Engineering Radio. Today I'm speaking with Spencer Dixon. Spencer has been building websites for over 10 years and is the CTO at Tuple, a screen sharing application for pair programming. I'll be speaking with Spencer about building Tuple using Webrtc and the many challenges that come from building a native application that requires low latency and video communication. Spencer, welcome to Software Engineering Radio.
Thanks, Jeremy. I'm really excited to be here.
First, could you give a quick introduction to what Tuple is for our listeners?
Sure. So Tuple is a remote screen sharing application, somewhat similar to Skype or Zoom or Slack calls. However, it's purpose-built for remote pair programming specifically. So all of our design decisions rely around making the best possible pair programming experience that we can.
One of the things about Tuple is that you used Webrtc to allow for the screen sharing in order to see each person, in order to see each person's screen and all that. Before we go into the specifics of building Tuple, I kind of wanted to set up what are the pieces that are in it. So to start, what makes Webrtc different and what is it used for?
Sure. So it probably makes sense to give a high-level view of like what Webrtc is before going into what it's used for. It's really three things. It's a spec, which provides information on specific APIs, and then there's also the implementation side of it, which can be found in libwebrtc, which is this massive, 5 million plus line C++ code base.
Wow.
And all of the major browsers use that libwebrtc to implement the spec in their respective browsers. So Google, Mozilla, Opera, and those APIs allow you to share any sort of real-time media. But it doesn't have to just be media. So one aspect of Webrtc that's pretty useful is the concept of creating data channels. So you can establish this connection between two peers and then really send whatever bytes of information you want from point A to point B, which has some interesting use cases. I know people have built like BitTorrent clients using Webrtc, but its primary use is for capturing frames from the webcam or your screen buffer and sending them over to the other peer.
For the data channel you referred to, is that for everything that goes over Webrtc, or is that only for specific types of data?
Yeah, the data channels will send data through SCTP, and the audio and video data gets sent over RTP. And RTP actually is really two things. It's Rtp and Rtcp. So there's the real-time protocol and then the real-time control protocol. And Rtcp allows the two peers to kind of send diagnostic information as to how the stream is going, so that way they can update in real time. And I believe that Webrtc actually uses some sort of extension to RTP, which allows it to send both those two protocols on one port instead of, I think traditionally RTP, you use one port for the RTP and then you increment it by one, and that's what Rtcp gets sent on.
You said it allows it to use the same port. So then are those two separate connections then to the same port?
Nope. So it's one connection that all this kind of gets multiplexed over, I believe.
You mentioned so Rtcp, that's once two clients are connected to one another, kind of updating on how the stream is going. Would that allow for things such as like if one client is getting a little slow, that they could talk to one another to say like, oh, I'm going to lower the video quality? Or is it more for just like, hey, things are going bad, but there's not much you can do about it?
Yeah, that's a good question. I think at that level of the stack, it's not making any intelligent decisions like that. Most of those decisions are happening a bit higher. And that's part of the magic of the Webrtc video and audio pipelines. They're listening into those RTCP responses to kind of get an idea of how much jitter there is in the network, how the packet loss is, and adjusting the situation to be optimal for that.
Cool. And you were saying that RTP, that's where the actual video and audio data is. That's how that's being transmitted.
Yep. And that's built on top of UDP, which is, so it's UDP and then DTLS. So DTLS is Datagram Transport Security Layer, or Layer Security. It's the equivalent of TLS in the TCP world, but for UDP. So it's very important that, all the packets are encrypted and somebody can't, listen in. And then the packets after DTLS go through SRTP and SRTCP, which is just the secure version of those. A lot of protocols.
Yeah. And so like UDP, it has like no guarantees in terms of you send a packet via UDP and the other.
Right. So there's no reliability in the order that packets are going to be received. So they can be in order or out of order. And then you also no longer get certainty that the packet will have arrived. In TCP, you do get those things. You're guaranteed to get packets in order. And if their packet gets lost, it'll do a retransmission and you'll receive the packet. The real reason that UDP is much better for this situation is because it's a lot lower latency, but it also means that the Webrtc pipeline has to do a tremendous amount of work to make up for error correction, or in some cases, it even will ask for a retransmission of packets given the current context. So like if it's going to be cheaper to ask for the retransmission, so let's say the round trip time between peer 1 and peer 2 is very low, oftentimes it'll be cheaper to just ask to retransmit the packet than do something else. So the data channels which use SCTP, that's the main reason why they use SCTP, is to be able to kind of configure the data channels to be in a reliable state if you wanted them to be. So I don't actually know too much about stream control transmission protocol, but the easiest way to think about it is it allows you to simulate a TCP or TLS environment using underlying UDP packets.
Okay. SCTP, that would be something that you would use maybe if you didn't have such a low latency requirement, or when would you use that instead of using RTP?
Yep, that'd be one example. Or, for Tuple, there are certain messages that we want to make sure no matter what, they go from point A to point B. And so our data channels are configured to be reliable and send those messages in order. For example, imagine if you were moving your cursor on the host's machine and the packets started coming in out of order. That would look super wonky if you saw the cursor jumping all over the place from, point A to point B. So we want to make sure that those messages are getting sent in order. And the fact that they're reliable is maybe a little bit less important, but the in order aspect for that use case, for example, would be something that we care a lot about.
And is that because in the case of audio and video, there is sort of something higher in the stack that's taking care of things that are out of order or things that are being dropped? Whereas in the case of the moving someone else's cursor example, there isn't that sort of thing in place. Is that kind of the thinking?
Yeah, I think that's the right way to think about it. So the cursor example, that's very much at the application level. So Tuple, we've come up with our own protocol for how we want to send cursor data. We do some fancy stuff like caching to make things a little bit quicker. But for the most part, that's all defined by us, where the audio and video stuff, that's all being handled by Webrtc. And Webrtc has a number of different buffers along the pipeline that enable it to fix out of order packets and then also allow for smooth playout. So for example, like one of the core abstractions in Webrtc is the concept of a track, like a media track. And a track could be audio, it could be video, it could be the screen. And if you associate an audio track with a webcam track into a stream, then Webrtc does all of this magic for you where it'll properly buffer the audio and the webcam, and then the playout will occur so that way, the person's mouth actually looks like they're talking instead of it being totally off. So it's somewhat of a double-edged sword. Like sometimes you don't want that, right? For Tuple, for example, we actually don't care if the audio is synced to the screen, care more about lower latency. And we want that as soon as you click a button on someone's screen, you see that feedback. So we intentionally disassociate the audio track with that specific video track in Tuple in order to get some latency benefits from there.
The other thing, like when we're talking about audio and video being handled by Webrtc, there's a concept of a codec. So could you explain like what a codec is?
Sure, yeah. Codec takes in a raw image and compresses it to as best as it can based on different parameters. You kind of specify what you care about. And then part of the codec is decoding. So that's the encoding stage. Then it gets sent across the network through Webrtc. And then there's the decoding stage where it takes that encoded frame and brings it back to its original form. Sometimes they're lossy, sometimes they're lossless, depending on what settings you have and different codecs are better at different things. For example, like H.264 is not as good at encoding very, very large frames like 4K displays compared to something like VP9.
So how did you decide which codec to choose when you were working on Tuple?
That's a good question. So Webrtc already has a number of codecs built in, or rather like implementations of using the codecs. And we tested out VP8, VP9, H.264 with all sorts of different settings. One of the big value adds for Tuple is we allow you to send the full resolution of your display if you want to, which turns out to be very useful when you're reading small text in a text editor, for example. So in doing those performance tests, VP9 just outperformed all of the other ones like significantly on these higher resolution screens. And so that's why we went with that. VP9 is just a newer version of VP8. And then the VP10 actually got merged into what's called AV1. There's a whole bunch of big companies who've kind of merged together to build the next generation of codecs, because codecs are one of the most complicated pieces of software in computer science, probably. And any one company doing it by itself, it's just a lot of work. And so Google was generous enough to kind of offer, their resources and the current work they had going for VP9 to merge it into this new consortium. We are actually in the process, or I'm in the process of looking into using H.264 hardware accelerated encoding. So that whole process I was just explaining, there was a built-in assumption in my explanation that this was all happening at the software layer. But a lot of devices actually have hardware implementations of that encoding step or the decoding step. And so Macs do have H.264 hardware encoders built into them. And so now that we have introduced the webcam into Tuple, which for a long, long time it was just the screen, there's definitely a lot of optimizations we can do by pushing some of that load from the CPU over to the GPU. And the plan is to hopefully get hardware accelerated encoding working for those webcam streams, because those we don't let get very big. I think the max resolution on those is like 320 by something, 240. It's small. We only have a small little webcam.
So if I understand correctly, then you would capture someone's video from, say, a camera, and that imagery, is it originally in an uncompressed format, and then you have to take that uncompressed imagery and compress it using a codec. But if the hardware of the machine, like say on a Mac, has hardware support for H.264 or something else, then the GPU can actually perform the encoding and decoding instead of the CPU.
Yeah, you got it. So in some of the webcams, they actually will have encoding built into the webcam. So you get an encoded frame already, I believe, but that's not like a use case that we're worried about at all. What you explained is exactly right. And for example, on most iPhones and phones, they all have H.264 hardware decoding, and it's very useful for extending battery life, which is part of the reason why they do it.
And does that apply also to desktop capture as well? When you capture the screen and you send it over the wire, that's also going through that same encoding process?
Yep. Same general concept. Capturing the frame. The capturing step is, there's a tremendous amount of optimizations that occur there as well. Luckily, Webrtc actually already had a pretty good Mac capturing setup, which I believe they actually grabbed from Chromium. There was a couple bugs in it we had to work out, but instead of capturing the entire frame buffer, what it does is it listens for like diffs. So it'll keep like a local version of what the frame buffer is, and then whenever things change on the screen, it'll receive a callback. Like this is a low-level display stream callback in Mac OS, and it'll get that diff, and then it'll update its representation of what the frame buffer looks like, and then it'll pass that along to the next step, which then goes to the encoder to be encoded and sent across the wire.
Interesting. So in the Webrtc library's implementation, they have sort of already done the work to hook into all these different operating systems and have the operating system tell them what's changed on the screen. So that's the only part they have to send. Is that right?
Not entirely right. So let's kind of break that down. So yes, WebRTC provides lots of default implementations for a lot of the big core components that you end up needing. And that capturing part specifically, which you were just talking about, it does send the whole frame to the encoder. And then the encoder actually is in charge of doing lots of very intelligent temporal and spatial diffs to figure out what's changed and then only send the pieces over that have changed. But more what I mean is in the capturing phase, instead of it'll just look for the screen updates and update the diffs in that specific part of the pipeline, if that makes sense. I don't know. I'm doing a bad job of explaining it.
I think let's see if I was understanding correctly. So the part where it's checking for the diffs, that's specifically at the capturing stage. So it has like, I guess, a frame that it knows like, okay, this is what's currently on the person's screen. And in order to update that capture, it's hooking into the operating system. Is that correct?
Yeah, that's right. So that allows the capture times to go from, tens of milliseconds to sub 10 milliseconds, because if you had to capture a very big 5K display, the original display stream APIs that Mac provided didn't have this sort of diffing available, and it might just take a significant chunk of time to do that. Like, give me everything that's on the screen right now, where their capture kind of has some intelligence built in to not need to do that, which is nice. There were some things in their capture actually in the early days that really hurt us from a latency perspective. So they have this concept of like window exclusion. So let's say I want to capture the entire screen, but I don't want to capture, the window that has the webcam on it, so the other person's face. Well, their exclusion code was somewhat naive in the sense that it would iterate over all of the windows on the screen and kind of like recreate the pixels that would be behind that screen that you want to exclude. And that actually ended up being very slow depending on the size of the exclusion and how many windows were on your display. So we've had to do some things to kind of tweak and optimize that. In the specific webcam instance, what I do is I actually capture the frame as normal with the webcam on it. And then I go to that pixel buffer, which is just, a big array of the bytes of the pixels. And I just turn all of the ones that the square where the webcam is, I just turn them all to a different color. And so that way and I do this before even going into the encoder. So that way the encoder is not worried about trying to encode two different types of video, right? Like there's the screen video and then the webcam video. And there's lots of different optimizations that encoders can be tuned to do well in one scenario versus the other scenario. And we've spent all of our time in like testing, trying to get our VP9 implementation to do very well for the screens. And so by sending in a video on top of that, it does us a disservice. So I kind of like get around that problem by whiting out those pixels before feeding it into the encoder.
Right. So the WebRTC, I guess, screen capture part is you're allowing it to capture the whole screen and capture the sort of webcam video, and then you're sort of going into there, blanking out all the pixels where the webcam window is showing, and then you send that over to the encoder, and to the encoder it looks like nothing has changed. It's just always this box. And
white box, black box, whatever color. I actually changed the color based on if they're on Mojave, if they're in dark or light mode. So I try and make it look, good for whatever mode they're in.
Oh, nice. It's pretty slick. Another part of WebRTC I want to kind of go into is there's this idea of a session description protocol. Could you kind of describe a little bit about what that is?
Yeah, really this gets down to like the establishing a connection between two peers. The overall protocol is called ICE, so it stands for Interactive Connectivity Establishment. It might make sense to go through an example of like how a normal call would start. I haven't used the JavaScript APIs in like over a year since when we first started working on Tuple, so I might get this a little bit wrong, but do my best. So initially, you want to create a peer connection, and you pass into that peer connection constraints. And so the constraints are, I want audio or I want video. And this is really the power of WebRTC, the fact that you can just say video true at the JavaScript layer, and it just does all this magic to figure out how to capture the video and set up the encoder for you. You don't need to do any of that in the JavaScript API. So once you have your peer connection, before even that, you need some sort of what I like to call application signaling. And that's a process where, let's say we have Alice and Bob, and Alice sees that Bob is online. She needs some way to ask Bob if he's ready for a call right now. And however she wants to do that is fine. Like most people end up using a WebSocket server, and she just sends a message over to Bob, and Bob can accept or decline. But assuming, Bob is ready to go and he accepts, then Alice she'll call navigator get user media given those constraints. So this will signify to the browser like, hey, go ahead and get those capturers going, start getting frames from the screen or start getting frames from the webcam. And once it's got those frames, it'll give back some media tracks. And then Alice can add those media tracks to her peer connection and then create the initial offer. So when she creates the initial offer, that's when the SDP gets created. I know there's a million acronyms, I'm sorry, but the SDP is basically just this really big string of super esoteric like letters and colons and magic numbers that will tell Bob, what capabilities Alice is looking for in the call. So for example, things that are on there might be, she's trying to do video, she's trying to do audio. And inside the video section, it might say her computer is capable of doing VP9, VP8, or H.264. So if Bob only has the ability to do H.264, maybe he's on like a phone or something, then the Webrtc will allow them to negotiate this session with just H.264. So that's really the whole point of the SDP, is for the two peers to be able to share like what their capabilities are and preferences. So you can also explicitly say like, in this call, I want to use, this encoder implementation. She calls create offer, that SDP gets generated, and pretty much every single step in this process is async. So you kind of have to wait for callbacks to get called. Once she gets that offer, she then needs to send it to Bob. And how she does that, again, doesn't really matter. She could write it down on a piece of paper and send it to him, and this process would still technically work. I've messed around with some Webrtc stuff where I just copy and paste this SDP from one computer to the other. So this part is totally left up to you as the developer and application builder. Sends that to Bob. Bob will set that SDP as his remote description, and then he will create an answer given that SDP. And once that answer gets created, another SDP is generated on Bob's side, and Bob will set that as his local description and then send that back to Alice. And then once Alice receives Bob's SDP, then the process enters into this ICE interactive connectivity stage. And yeah, so what happens there is on each Webrtc client, there's what's called an ICE agent. And the ICE agent is responsible for gathering what are called ICE candidates. So an ICE candidate is just a IP port pair. And the first thing that the ICE agent will do is it'll gather all of its local candidates, and then it uses a process called stun to gather any remote candidates. So stun servers stands for session traversal utilities for NAT. And it's really a tool for NAT hole punching, which I think was originally created by like video game developers, but I could be wrong. But stun servers are very simple. You're basically just making a request to this server that's publicly available on the internet. And that's very important. Like that server has to be publicly available on the internet. And the server just responds back with what IP and port you made that request with. And Google actually hosts a stun server that most people use in the early days to get going with Webrtc. It's very highly recommended to not use Google's stun server in a production environment, because for all you know, it could go down one day and then none of your users will be able to connect and make calls. For Tuple, we actually pay Twilio for access to a stun and turn server. All right, so the ICE agent on each peer has gathered the local candidates. They've gathered the remote candidates through making requests to the stun server. And then the final step is like what's called connectivity checks. So you have this array of these ICE candidates, which are those IP port pairs, and it organizes them based on a set of priorities. And as a developer, you do have some say in that priority if you want, or you can just let Webrtc make an intelligent decision. Generally, it's going to try and start with the local candidates first, and it's going to fall back to the remote. And then the final candidates it'll use are what are called turn candidates. So, sorry, this is so much, but turn is a way for the two peers to still have a call if for some reason they can't establish a connection peer-to-peer. So a turn server just relays packets from point A to point B. And for the most part, I think all turn servers are also stun servers. Like, I think it'd be weird to have a turn server that didn't also implement the stun protocol. It does those connectivity checks where the two peers try and communicate with each other based on that ordered list of ICE candidates. And as soon as one is successful, then the connection gets established. And throughout the call, that might change. Maybe the network path that was chosen ends up being no good anymore. And so the ICE state will change throughout the course of a call to disconnecting, for example. And as an application developer, it's your responsibility to, pop open a reconnecting window or let the user know that the call is not connected. And oftentimes ICE will recorrect itself. So it'll just keep going down, that prioritized list of candidates until it finds one that's good. And if you have turn set up, it is optional. You don't have to have turn set up. And it does cost a lot of money because you have a lot of bandwidth going through these turn servers relaying, potentially big frames of media data. But eventually, if you have turn, it should always connect because the turn server is always publicly available on the internet. So if a peer can't connect with turn, it means they have other issues going on, most likely.
So let me see if I can unpack this. So to start, you have the sort of initial file that describes what kind of codec and what kind of bandwidth is available to each client, and like what sort of IPs and ports they have available. And so that's both peers have to create a file that has this information. And then you need some way of sharing this file outside of WebRTC. So you said that could be through WebSocket, or like you said, you could even just copy and paste the text, right?
Yep.
And then you mentioned how there's a stun server, and that is because it's sometimes machines can't connect to one another directly, and you have to find some way of going through the NAT of each user. And I guess the stun server helps to negotiate that.
Yep, that's right.
And then you said there's a turn, and I don't remember what that acronym is, but
it's traversal using relays around NAT.
Okay. And so if the two users are unable to establish a direct connection through the stun server, then the video or the audio data will go to the turn server and then will be streamed from the other client from the turn server. So it's no longer a peer-to-peer connection.
Yep. Yeah, you got it. And the turn servers are pretty dumb. They just relay, the packets from point A to point B.
So in the case of Tuple, do you establish a peer-to-peer connection first and then fall back to a turn server, or what does that look like in Tuple?
Yeah, that's always the ideal case. And for, real world metrics, I would say anywhere in the range of 88 to 94% of the connections can be established without turn. So it's very low percentage that end up actually needing turn. In the early days, we actually did not support turn, but then occasionally, we'd get support tickets with people saying we weren't able to connect. And to be honest, the experience when you're using turn it's not fantastic because you're adding all this additional latency, but there is a certain level of importance in just being able to let the clients connect, even if it isn't going to be the greatest experience. At least they're able to collaborate a little bit or even like have some audio going. So we use Twilio for that service. We don't manage our own turn servers. There are very popular open source libraries. I think CoTurn is the big one. And then there are other companies that do hosted turn servers for you. I think Xerxes is one of the other big names. But we had all used Twilio in the past for other companies, and we're familiar with their docs and APIs and stuff. So we set that up. And as far as when in the process you need to configure turn, when you go to create a peer connection, you can pass in a configuration object, and that configuration object will have the URLs of the stun servers that you want to use. And you can use multiple stun servers, so it can back up to one if one is not reachable. And you also provide it with the turn URL. And so when we go to create a call, first we have to make a request to Twilio and get a new auth token to then pass in for that turn URL.
And this information about stun and turn, is this embedded into that text file you're talking about that has all the codec metadata and so on?
No, so there's actually two parts of it. So the SDP gets created that has all the media information, and then once you've set, I believe, I'm not 100% certain, but I think once you set the remote description, that's when the ICE agent kicks in and starts generating these ICE candidates. And so you'll have this callback that's like on ICE candidate essentially, and you are also responsible for sending each of those ICE candidates over to the other peer because they both need to have that list in order to do the connectivity checks. And there is another thing, just to make this even more confusing, called trickle ICE, where in the original ICE implementation and the early days of WebRTC, the time to connect calls was very slow because both the ICE agents needed to collect all of the possible ICE candidates before starting to test them and see if they were able to connect. But there was a new spec released a couple years ago at this point, I think, that allowed the ICE candidates to start checking a little bit sooner, like kind of like just in time, like as they're coming in. And so that speeds up the connection process significantly. And we do that. So we do what's called trickle ICE. So as soon as we get that ICE candidate, we send it to the other peer so that way they can start testing them out and seeing if they're able to establish a connection with each other.
Cool. I think that's like we've got a pretty good overview of sort of what WebRTC is and sort of what the different pieces are. So next I want to sort of go more into building Tuple specifically. Tuple is, like you said, it's a pair programming application. So you have the webcam capture, you have the desktop capture, you have remote control of each other's machines. And then, of course, as with any SaaS application, you have billing and accounts and so on and so forth. So when you first started working on Tuple, how did you decide what to build first?
It's a good question. I think in the very early days, it was a lot about just validating if we could do certain things. So, for example, one thing that was very important to us is as a developer, I constantly use Command Tab to cycle through my various applications.
Yep.
And so we wanted to validate, like, can we remotely send a Command Tab from machine 1 to machine 2 so that way they can feel as if they're local. So that was like something we wanted to validate very early on. And even before that was, can we even, establish a connection between the two peers? Luckily, WebRTC actually makes that initial spike phase very fast. Like, I think within our first weekend of kind of getting going on Tuple, we had like a real screen sharing app that sent the screen from A to B and you could move the mouse around. The thing was that was all in Electron in these very high level JavaScript APIs, and the performance was not nearly as good as what we wanted.
When you're referring to the performance, is that the latency, or what was the part that was an issue in the browser?
Yeah, latency and quality. There's a lot of constraints that, let's see, what's a good way of explaining this? So WebRTC, like I said, is this, very, very large code base. And they expose a lot of things with their APIs, which allow you to hook into the system. For example, like creating your own video encoder or doing the capturing on your own. But there's also a lot of parameters that are built into that video pipeline and that audio pipeline where the browser just made certain decisions because the browser has its own goals, right? Like the browser doesn't want to use up all your resources. People already complain about, Chrome using up a high percentage of their CPU. Well, there's certain things that Chrome, in the way that they use libWebRTC, they ensure that, the CPU gets throttled. And if it's using a certain amount, then it's going to downgrade the quality of the stream or, make certain trade-offs. And we recognized very early on that, like, if we were going to use WebRTC in the context of Electron, we just weren't going to be able to push the needle as far and as fast as we wanted to. And that's really what kind of led to us extracting out, that initial spike into C++ and a Swift implementation.
So it's basically Chrome or the web browser they have their own WebRTC implementation, or they're using the library, I guess, that was created in C++. Is that correct?
Yeah, so Chromium will use libWebRTC, and then they'll kind of tweak certain settings. And like, for example, a classic one is they have a bandwidth cap. Like each peer connection, I think, can only have 2 megabits per second bandwidth. So like we first thing we did was increase that cap. And just doing that allows us to send a higher quality frame. And most of the time, that's just fine because people, or at least for our target market, they have good internet. So that cap doesn't necessarily, they don't care about that, right?
Mm-hmm. Is that something that you don't have control over when you're running in, say, Chromium?
Yeah, or just the JavaScript APIs. The JavaScript APIs are very high level. You don't really get much control. I mean, it's a blessing and a curse. Like, you're able to get something going very quickly, but as soon as you start wanting to do something very specific, you run into these pain points where, like, if we wanted to continue down the Electron route, we probably would have had to build a custom version of Chromium with our custom version of WebRTC that then we built a custom version of Electron with that custom version of Chromium, if that makes sense, which we could have done. And looking back at it now, it'd be interesting to see what that would look like. But it would have taken a long time. It would have just been a real big pain to do, honestly.
Yeah, I mean, I guess it's sort of the sort of thing where you start going down that road and you're not sure what you can or can't do or whether it was a good idea until you really try it, right?
Yeah, and then I know Chromium has this whole concept of sandboxing, and so I imagine if we had gone down that route, there would be a lot of fighting with that sandbox environment. Like, there's a lot of things that we need access to and APIs that we wouldn't be able to distribute our app on the App Store, because even just to do that, like, command tab thing, you need pseudo privileges essentially to be able to do that.
Yeah, I think I remembered hearing that Screen Hero, which was a screen sharing application that came before, when they were acquired by Slack, they were kind of asked to like try and make it work as an Electron app. And it sounded like they had a lot of difficulties, a lot of struggles with doing that. So maybe native is the way to go.
Yeah, no, for sure. We talked to those guys. Like, we definitely think of ourselves as the spiritual successor to Screen Hero. Like, we were 100% inspired by them to build this company, and we're very friendly with their founders, and they've given us a lot of tips and advice over the year or so, and we're very grateful for that. Don's helped me with some of my mouse implementation stuff, and Faraz has given us good tips on other things. So
very cool. Kind of after all this, you first started, you experimented with using Chromium, using the JavaScript APIs, and then ultimately decided to move towards building a native app.
But yeah, it's interesting. Like, from going from Electron, the first step was actually the next step was going to Swift. We actually didn't want to do any C++ stuff. So at the time, we hired somebody to help us fix the Webrtc Mac Sdk. So there was actually already like a pretty well built out SDK in Swift and Objective-C for interacting with these low level C++ WebRTC APIs, but it wasn't working. Like, it wasn't compiling. That's been a common thread, unfortunately. And my usage of WebRTC is oftentimes the Mac. The Mac stuff kind of they don't really ensure it's always up to date or going to work properly. There's a lot of that's kind of been put on us. But yeah, so we originally hired him his name was Sam. He was one of the first engineers at Sketch, actually, Sketch.app, the prototyping tool. And he built like a WebRTC framework for us, which we then used for a while. And even that, we decided we didn't have enough customization over the different parameters that we wanted, and that we'd have to go another layer deeper.
The WebRTC Mac SDK, is that something that is built into the operating system, or is that a open source project? Like, where's that coming from?
That's coming from libWebRTC. So they have Objective-C bindings to all their C++ code. And one of the beauties of Swift is you can bridge Objective-C to Swift relatively easily. And so we were able to call into those C++ APIs through Swift doing that. In Swift and Mac development, Cocoa development in general, their libraries are called frameworks. And so Sam basically built us this like WebRTC framework that we were able to use to get going in the early days. And I'm honestly very grateful looking back that was the progression, because prior to Tuple, I've only been building websites my entire life. I'd never built a native application before. And there's a whole lot of stuff to learn in just building Cocoa applications and Mac development in general. And so by getting this opportunity to kind of like ease into it, I mean, I was definitely very stressed at the time, and but if I had to jump into the C++ at that point, I would have been way too stressed. I don't know what would have happened. So getting comfortable with the Mac development first and then going into the C++ stuff was a good progression, I would say.
Yeah, so let's see. There's the libWebRTC, which is a C++ API, and they provided an Objective-C wrapper for that as a part of the official project.
Yep.
But it sounded like that wrapper
was somewhat out of date.
Yeah, okay.
So for perspective, WebRTC has like 200 commits a week on the project, and it moves really, really fast. Especially, I think in the early days, it was moving even faster than it is now, but they'll often change like the correct way of doing things. So even in the 1 year that I've been working in it, they've changed how to do some of the like track and stream management. So like we've had to kind of like, adopt the new practices for that. And a byproduct of that is if they're changing things a lot, the SDKs don't always stay up to date. So Sam, who was already an expert in Objective-C and Swift, he helped us kind of get that caught up for our needs, essentially just porting over the specific APIs we knew we needed at the time to be able to get the calls going and everything. Looking back at it, like there was a ton of things that we now use from WebRTC that he didn't port over. So, it's good that we now are just able to do that ourselves. And whenever we need new stuff, we write all of this glue code to make it work. There's a surprisingly large amount of glue code between different languages in Tuple. I think altogether we have 7 different languages that we use,
wow,
which can get somewhat confusing for my brain sometimes.
So that's that's pretty wild. So you said you had a background just in building websites and web development, and now you're in an environment where you're working with 7 different languages. So I guess how did you tackle that? How did you start piecing together, what to learn and how to do that?
For me, the way I learn best is through reading books and building little sample projects that test the knowledge of the books that I read. And then I'll often go back and reread the sections that were confusing to me or that I think are important for me to know better. So a lot of that, I probably read like 50 or 60 books this last year.
Wow.
I have like stacks and stacks of C++ books, Cocoa books, Objective-C books, Swift books. And then as I was reading them, I would build static site generator and Blackjack were usually my first 2 projects in each language. I think static site generators are actually like a very good, like get your feet wet into a new language type of project because it involves networking, async stuff. It involves reading the file system, involves templates, and basically all the main things you touch in a language, you kind of get by building a static site generator, especially if you get like, parsing command line args and all of that. So that was my main strategy. Then once we started getting some revenue, which was awesome, Ben did an amazing job of actually pre-selling some Tuple before we even had the product. We used a lot of that money in the early days to consult with experts. So a couple of people, that Sam guy I told you about who worked at Sketch, he kind of helped get the initial Xcode project set up. And, there's this thing whenever you change languages, after you've done a project or 2 in that language, you have, more opinions on how you would set up the structure of the project. Once you know the ecosystem better. And one thing I just didn't know anything about was Xcode or how to properly set up, packages to be libraries and stuff like that. And so Sam kind of helped guide us in that, which it seems so simple and silly to have paid someone for that looking back. But like now I know all of that stuff very well, but it gave us a lot of confidence knowing that we had a strong foundation and that, the frameworks we were building to be reusable and stuff were set up properly. Yeah, lots of YouTube videos, talking to experts, building lots of side projects, and kind of taking like one topic at a time and trying to isolate it from the rest of the parts. That was very useful.
Basically, reading a ton of books, building small projects, having some consulting help. One thing I did want to ask too is about WebRTC specifically. Were there any specific resources you used, or did you have someone you consulted with to learn about that?
Yeah, unfortunately, the resources for learning WebRTC are not the greatest, I would say, compared to, especially if you're coming from the web world where, there's somebody who has written some sort of ebook or tutorial series that you could just buy for X dollars and kind of level up on that topic quickly. For WebRTC, the best source of truth is just reading the header files. Really, most of what I know about native WebRTC has been from reading the code. That's not a great answer, and I hate when people give me an answer like that. So some other good resources are WebRTC Hacks. That's forget the gentleman who runs that, but we had lunch with him at one point in the early days, and he gave us some good tips and resources as well. Cosmo Software, Dr. Alex, he's a PhD in video encoder. I think he has like multiple PhDs, and he's been doing WebRTC since the early days, like 2012, 2013, something like that. He's extremely knowledgeable. He's very prolific in the Google groups. So there's like a WebRTC Google group, and he's always answering questions and helping beginners. And so I would definitely recommend, not being shy in that Google group. And people are generally pretty nice as long as you've done your research and or provide, good examples of what you've tried and what hasn't worked. Then people are, very, very willing to give you some tips. And yeah, I guess just if you're working at the higher level of abstraction, the Mozilla docs are really good. So the Mozilla docs have some great examples of how to use the various JavaScript APIs. There's a fantastic book called High Performance Browser Networking. I forget the author's name. I think it's like Igor or something. That has a good section on WebRTC, and just in general is a great book for anybody who's doing networking or web development. Talks a lot about TCP slow start and various things to improve the performance of your web apps.
Cool.
Yeah. So yeah, those would be my go-tos. That's a lot.
Yeah.
But honestly, just building stuff too. Just build some little side projects. It's a great way to learn.
Yeah, we'll be sure to get all these links into the show notes.
Definitely.
The other thing I guess I wanted to ask about is you mentioned that you're using 7 languages. So I kind of wanted to get a better picture of why are there so many languages involved in the project?
I think that the main reason why we have so many languages is because we had certain expertises in prior languages, and therefore we were a lot more effective at building parts of the application in those languages. A lot of the decisions we made, it's very clear that like this language is the best for doing this type of thing, and therefore that's why we should be using it for this. But there are like some situations I would say where if I had just already been an expert C++ developer, like maybe I wouldn't have done so much in Swift or Objective-C, right? But yeah, so like we have Ruby for our backend APIs, Ruby and Rails, and we were all Rails developers, so that made sense. We can move quickly. We have JavaScript for our partially on the backend side. There's a little JavaScript, and then also our UI inside the application. I basically ended up building a Electron inside of our app that lets me call JavaScript code and Swift code together. It kind of bridges those. And the primary motivator behind that was I originally started off building all these native NS views, and it takes a long time. Like if you're coming from a web background where you can spin up, a basic website with some CSS in an hour or 15 minutes, and then you go to this native world where it might take me an entire day just to build a button that like kind of looks not like what I actually want it to look. The difference in that time is drastic. Like I do think that one day Tuple's entire UI will probably be native, but we wouldn't have I don't want to say we wouldn't have survived as a startup, but if it would have taken so long to get to the UI to where it is right now if I hadn't just written it all in JavaScript, which I know and I'm very fast in. Like our current UI probably took me like a weekend to do. That was like the least time sink out of the entire project. And then the Swift, because it's a lot more fun and fast to develop in Swift than it is Objective-C or C++. So we try and do like the minimal amount of C++ and C code that we need to interface with these low-level APIs, because a lot of APIs are just easier to interface with in C++ or C, or we're communicating a lot with WebRTC. So it makes sense to kind of keep that code all co-located. And then Objective-C and Objective-C++ are what allow us to call into the C++ libraries that we have in Objective-C. And then that Objective-C gets bridged over to the Swift. So I think that's all the languages. Let's see, Swift, Ruby, JavaScript, Objective-C, Objective-C++, C++, and C. And then, like CSS and all that.
Right. So that's kind of interesting. So it's the actual UI of Tuple is primarily a web view then, it sounds like. And then you're using Swift, I guess, to communicate, I guess, with the operating system level APIs when possible. And if it's not possible, then you kind of go down into Objective-C or C just based on whether or not the API you're talking to is written in C or C++.
Yep, that's essentially how I would think about it.
And sort of, I guess, in the end, like when you look at all the code that you've written for the project, what is most of the project written in?
It's a good question. I can probably have GitHub just tell me when I look at the thing. All right. So 40% Swift, 20% C++, 20% CSS, 10% JavaScript, 10% Objective-C, 5% Objective-C++, 1% other. So probably like text files, README files, documentation, stuff like that.
Interesting.
It's a big breakdown. And that's just the client app, by the way. Like there's also the backend app, which is the Ruby and Rails app and stuff.
That's right.
That's just the one that I'm, working in most of the time.
So the parts that are written in Swift versus in C++, I would guess the C++ parts, it's probably working with the lib Webrtc. Is that correct?
Yep, lib Webrtc, and then there's another C++ library we use to help out with some like mouse coordinate stuff that I also use C++ for. No, yeah, you're right. Primarily, most of the C++ is us creating our own utilities around Webrtc.
And then you said 40% is Swift. So like what is most of that Swift code doing?
Rendering the UI, doing diagnostics, handling different mouse modes. So in the app, we have different cursor modes, which allow people to, point out specific things. Yeah, just like all of the normal things involved with getting an app, like a native macOS app running. There is a lot like authentication, talking to our API, handling feature flags, so only showing certain features to certain people until we've kind of validated that they're going to be good. Handling like deep linking is the most recent thing I've been working on. So being able to, start a call using a special tuple URL, which enables things like Alfred integrations or Slack call integrations, talking to our analytics service to get an idea of, what features people are using and what we should be focusing on. I think that's most of the stuff I can think of that the Swift layer is doing. I mean, there's also the Swift layer manages like the state of what the UI should look like. And then it just sends that state across the JavaScript and the JavaScript renders it appropriately. So there's a good amount of code dealing with that. Then there are like a lot of windows that aren't WebKit views that are native windows, like the preferences window for like changing various things throughout the application. So when we can, we want to use the native APIs, and when we think it really makes a difference or it matters. So for example, when you're guesting and you're looking at the screen of someone else's computer, we use the native macOS toolbar that lets you change all the different cursor modes and the screen resolution, and we use all native controls for that.
Yeah, so it seems like Swift is really, it almost feels like it's sort of the heart of the application, with the exception of the C++ for the WebRTC interaction, and then you've got some of the web views for some of your UI components, but those are kind of like maybe the three main parts.
Yep. Yeah, that's a good breakdown.
Cool. I guess my next question would be, when you were working on the project, was there anything you found much easier than you thought it would be?
Yeah, I think that the call stats ended up being a lot quicker. So for some context, in the Tuple application, one of the unique opportunities we have, because our user base is primarily developers, they're somewhat technical. And so we actually expose the stats of the call while a tuple session is going. So you can see things like the frame rate that's being sent, the frame rate that's being output, how long it's taking to encode a frame or decode a frame, what the available bandwidth is. And all of these stats that are very useful if you kind of know this space and are somewhat technical. I created like a little dashboard interface to show that stuff, and it ended up being a lot quicker than I anticipated, primarily because Webrtc is so great. Like they provide these raw stat reports that they're getting from the Rtcp, which we talked about at the very beginning of the call. And yeah, that ended up being a lot quicker than honestly, I didn't even talk to Ben and Joel about doing that. Just one weekend, I was like, it'd be really nice if I had some dashboards to be able to look at what's going on in a call. So when I'm debugging things, I can figure out, when I change this setting, does this get faster or slower? And so that would be one thing that took a lot quicker. And another thing I would say is the webcam. I was very scared about introducing the webcam after we spent whatever it was, 10 months working on only screens, but it ended up being very quick and painless. And that's definitely a testament to, the Google engineers and Webrtc as a whole. And I think it definitely helped that I knew Webrtc a lot more intimately when I did that implementation. And I guess I should have realized that at the time, that like, oh man, I actually know a lot about this now, and it probably won't be too bad. but I was very scared at the prospect of having to add that into the application.
Yeah, was the main thing you were worried about, was it like the capturing from the webcam? Like you kind of weren't sure what that was going to be like, or what were you thinking, I guess?
I was worried about the UX of it, so how it would affect the current call experience. I was worried about the bandwidth concerns, so webcam eating up a lot of bandwidth, making the screen less reliable, or even eating up so much bandwidth that data channel messages get delayed, and then that experience, like the remote control experience, gets downgraded because of it. I was worried about just even the very basic things like adding the additional stream and getting it all set up correctly. At that time, I was using WebRTC in a little bit more of a naive way when it came to like establishing the connection. There's what's called a Transceiver Api, which you can get a little bit deep into. Most tutorials don't really talk about it, but basically a transceiver is an RTP sender and an RTP receiver, and you can set those transceivers up to be like bidirectional or one way. So can either just receive audio or can send and receive audio. And I had to do a pretty major refactor of how our WebRTC code worked in order to use those newer APIs that had been, like, when we originally had set it up, like there wasn't really any push to be using those APIs. Like it was fine to use the old stream-based APIs. So yeah, basically there was a big refactor that was going to touch major critical pieces of the code base. And that was really where a big part of the concern was. But it ended up working out great, and WebRTC is doing what it says it's going to do. So very grateful.
Nice. Yeah, I mean, it's sort of like you've kind of been talking about how there's so many things built into WebRTC that if the way they do it meets your use case, then it's kind of like, boom, you just kind of use it and you're good. And it's only when you're a little bit outside of what they do in the browser or whatnot that you have to kind of dive in and start doing something custom.
Yeah, definitely. And one day, I very much hope to actually not use the video pipeline in WebRTC and build a completely custom tuple pipeline. I honestly don't know. I have some ideas on how I would go about doing it, but I'm not confident enough in my abilities to think that I could do better than WebRTC is doing right now for us. I do think that there are a lot of trade-offs that WebRTC is making, which in our specific use case, we might not really want. So for example, they have a pretty big jitter buffer, which will ensure that if packets are missing or get lost, it'll just wait until it gets them. But in Tuple, what we'd prefer to do is just drop the frame completely at a set rate. And so it's if I'm not getting all the packets I need by whatever my target FPS is, then just don't even wait in the jitter buffer, just forget about it. And there are knobs and whistles you can tune in WebRTC to kind of make those decisions, but having complete control over it all seems appealing to me. So one day maybe we'll kind of get more in that direction, which would be awesome. I think there's a lot of low hanging fruit in the performance of Tuple still. It's just this last year has been so much of just leveling up all the skills we needed as a team in order to execute the V1. And now, next year is going to be a lot of improving the performance and adding in more and more unique features that just make the pairing experience even better.
Yeah, it sounds like you've built up this really solid base of knowledge, both in native development and in WebRTC and all that. And so it sounds like you guys are in a really good position to kind of go on to what's next.
Yeah, thanks. Definitely feels that way. I feel like a week worth of work right now was multiple weeks of work, even just 6 months ago.
Nice.
So the growth is compounding for sure.
One of the things that I believe you mentioned before is that you have to use some level of low-level graphics rendering or learn a little bit about Metal on Mac OS. Why was this necessary? Is this for the screen capture or what was that for?
No, so the Metal part is actually on the render phase. So the core reason why I wanted to learn about how that whole section of the process works is just because I think it's important to not have everything be a black box, and getting a basic understanding into how graphics and OpenGL works, the difference between a vertex shader and a fragment shader, how to send those shaders and your compiled program to the GPU. That's all stuff that I wanted to know enough about that it wasn't just this scary black box to me, if that makes sense.
Yeah, for sure.
And so WebRTC provided a Metal renderer already, and it's good. It works. There's I know for a fact, like when reading through the code, there's things I can do to optimize it a bit. There's some pixel conversions that don't need to be happening, like they're happening twice type of thing. But for the most part, there was only like one bug with it that we had to fix for Catalina. So I haven't had to do too much work on that. But the most important thing for me was being able to read that code and understand what was going on. And then also, I probably have somewhat of a selfish reason to want to learn it because one day I want to build a game engine. And that's a big part of building a game engine is figuring out how to do the rendering piece. So
nice. Yeah, I mean, I think like just in general, not even on specifically with WebRTC, like it's always good, I think, to go like maybe one level deeper than kind of where you're at, like at one level of abstraction, lower. And that way, if things are not working the way that you expect at the higher level, you kind of have a little bit of insight into what to do next.
Yeah, definitely. And I think learning about the whole rendering process and how metal works enabled me to be able to do that piece of code where I white out or black out the screen where the webcam is. Like I probably could have figured that out without that knowledge, but understanding at least a little bit more about how that whole subsystem works definitely made that be like a 1 hour thing instead of a 1 week type of thing.
For sure. If you were starting over knowing what you know now, are there any things that you would have done differently?
I think I would be less inclined to want to use Action Cable. We've been using Action Cable as our signaling service, and there's been a lot of like weird, wonky things with it, and it's very hard to debug. And I don't know. I think I would have preferred to just use like Socket.io or some other service that's maybe a little bit more mature in the wild or has been used in the wild longer. But that seems like relatively small thing in the grand scheme of things. I mean, in an ideal world, I wish I could start over and have all the knowledge I have right now about the space and the programming languages. The one thing I would say is I'm very grateful, like Swift, and makes it very easy to refactor like safely, which is great. So like as I've learned more about Swift development and Mac OS development, I've been able to kind of rejigger some of the application to be architected a little bit more effectively without, too much pain. Like if I was using something like Ruby for that, it would have been a lot more painful. But that's, I don't know. It's hard to say.
Yeah.
Don't have a good answer.
Right. I mean, hindsight is.
Yeah, hindsight's 2020.
Yeah. So, and also for the listeners, Action Cable being the WebSocket, I guess, implementation for Ruby on Rails, right?
Yep. Thanks for clarifying that.
And Socket.io being the equivalent for Node.js.
Yep. Yeah, I don't know. I'm pretty happy with the decisions we made. There's nothing like super bad that stands out. Like, man, if we had done this one thing differently, our life would be a lot easier right now. I guess the way that we set up the calls. So early on, we kind of had this idea that it would always be peer-to-peer, one-to-one, like you're pair programming with someone. What we didn't fully realize is that a lot of people do what's called mob pair programming, where they have multiple people in a session. But both Ben and I, who like have more of a background in pairing, like we never did that. We've always only paired like one-to-one.
Right.
And so a lot of the internals of Tuple was like very much set up in a way where it was only meant for two people. And I don't fully regret that decision because I would say that the code base was less complex by doing it that way. Like there was less that we had to think about, and it allowed us to get the app going a lot faster, and we were able to get to market. We were able to course correct and make these small changes that people wanted in order for us to become profitable and be able to do this as like a full-time thing. But if we had had funding and unlimited time, I probably would have bit the bullet and added that complexity into the app right from the start. And the complexity part being just the ability to start a call with like n number of people. But yeah, now we're kind of past that. Like the code base is set up in a way where that's no longer that much of an issue. So I don't feel too bad about it anymore. Yeah. But I remember at the time dreading that having to do that.
Yeah, I mean, in some ways though, it's probably it may have been good to start with just one-on-one because then it really helped you guys focus, right? Just on the one use case, make sure that use case is really solid and not kind of get distracted with things that not as many people use.
Yeah, 100%. Also, this is such a great example of, I don't know, product development, but so we felt like we were getting so many requests for doing n number calls and back in the early days when we didn't support that. Mm-hmm. And then since supporting it, like the percentage of people that actually do it is probably less than 10%. It's tiny.
Yeah.
And so like, I bet if we just didn't have that feature, it would still just be fine. Right.
Yeah.
But we would probably get some complaints about it. And really, like the challenge would be to keep a good psychological state and know that people are requesting something that like, they don't actually want or use that often. But yeah, it's funny how that works. Like a lot of people will be very loud about a certain thing, but then not a lot of your users actually end up getting value from that or wanting to or needing that feature. So
right. It's that's tricky because you don't know until you actually give it to them, right?
Totally.
So finally, is there anything you wish you had while developing the application? That could be a feature in WebRTC, that could be an open source library. Is there anything that would have made things a lot easier for you?
Yeah. I mean, this is not code related, but I wish I had multiple powerful machines sooner. So this sounds ridiculous, but like I had my one main laptop for programming on, and for a while I was just using these old laptops as like my peer number 2, peer number 3 while I was developing the app. And for a while I only just had like my one monitor, and then I used laptop screens. And like, I don't know why. I guess I was so worried about running out of runway because we weren't making money for a while that I didn't just invest in having, multiple monitors and like multiple brand new machines that are powerful.
Right.
And it's just like my dev life now is significantly improved now that I have that. So that's definitely a big regret, something I wish I had. As far as code goes, I really wish that if I didn't need to learn C++ to have made Tuple, I would think I would be a happier person.
Yeah.
That maybe sounds somewhat cynical, but I imagine C++ is great if you're really good at it and you've been doing it for a really long time. But the one thing I know about myself is like, I don't know. It's very easy for you to shoot yourself in the foot in C++, and I have made like all of the classic mistakes in C++, and it definitely makes me wish that there was like a Rust implementation of WebRTC or some other language. There is actually a Go implementation of WebRTC called Pion, not sure how to pronounce it, which is very exciting to me. Definitely worth checking out if you're looking for, trying to get your feet wet in more of like a side project-y type of thing with WebRTC, and Go or you like Go, I would check that out because it seems very cool to me. But it obviously it's not as robust as the C++ implementation that's been around for 10 years or whatever.
Yeah, it'll be interesting to see if there's, because I think like when people hear WebRTC, they're usually thinking of sort of the browser use cases, someone doing video chat or
sure,
audio chat, that sort of thing. And so it'll be interesting to see if more people are using it in kind of the native space, and if that sort of encourages the use of a binding in Rust, or like you said, building out more in Go, that sort of thing.
Yeah, I mean, even a full implementation in Rust, not just a binding, would be cool.
Yeah.
I think that if the Google engineers, and I know there's a lot of Mozilla engineers that work on WebRTC as well. I bet if Rust was what it is now, but back then when they started, they probably would have chosen Rust. But is what it is.
Yeah.
Maybe not. I mean, they interface with Chromium, so maybe they wouldn't have made that decision. But
that's true.
Trying to think of other things that I wish I had. I wish I had been more open to talking to experts early on. So I think there was a little bit of pride involved in like me not wanting to just use these resources like, oh, I need to figure it out myself. And every single time that we did a call with an expert on some specific area that I was interested in, the value that we got from that and the amount I learned was 10 or 20x how much we spent on it. And I think the next company that I do, if there is ever another one outside of Tuple, I'm going to allocate a budget towards talking to experts, but it's going to be a budget that I have to spend, right? So it's like, there's this much money in the bank account each month. Like it needs to be spent on somebody giving me some information. And the crazy thing is a lot of people just ended up helping us for free, even though we offered to pay them. And that's definitely something I've been very grateful for. I can't believe how many people in the community have like just offered their help or their expertise. I guess a lot of people just want to see this exist in the world, and that's been fantastic. But yeah, a dedicated budget to experts would be another one.
That's awesome. If you're stuck on something, sometimes just talking to an expert is like, makes such a huge difference. It could cut out like a week of time you would have spent struggling with something. So yeah.
Yeah. And when you're pre-revenue, like a week feels so long. It's so interesting.
Cool. Time
is trippy.
Well, I think kind of ready to wrap up, but is there anything else that you think I should have asked?
No, I think you did an awesome job. If people want to check out Tuple, they can go to tuple.app is our website. And yeah, my Twitter is my name, Spencer C. Dixon. So definitely reach out if people have questions or anything like that.
Fantastic. So Spencer, thank you so much for coming on the show.
No problem.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.